Hello, my name is Dr. Dale Weber. I am a research biologist with BEMCO. This presentation is about acoustic gate design, and it is intended to be both an academic and practical approach that should guide you when designing acoustic gates or curtains. Before we get into gate design, we need to first consider range test data. This graph was created from a simple long-term range test we conducted near our facility in Shad Bay, Nova Scotia. There are only a few ranges displayed, however you can still see that detection probability becomes more variable and decreases as range increases from a VR2W. This is a general plot shape of most range test data. When designing a solid or non-leaky gate, the goal should be to space receivers close enough such that tagged fish are detected in almost all conditions as they swim through. In this case here, for our example, we would suggest that range to this receiver would be approximately 350 meters when using a limit of 50% detection probability in the worst conditions. 50% means that one of every 2 tagged transmissions are successfully logged by the VR2W. Given the example range test data that we have just shown, it should now be possible to model the effect of receiver spacing on the ability to detect passing fish and be able to determine appropriate receiver spacing. When doing this, one should investigate detection performance in good and poor conditions. Here we show an example of range data during good and poor conditions. The red and blue lines are detection probability data generated from a range test for 2 receivers spaced 700 meters apart, one receiver at 0 meters and one at 700 meters as shown on the X scale. As you can see, for any given receiver in good conditions, a tag will be reliably detected out to 600 meters and in poor conditions to approximately 250 to 300 meters. The next question then is, given now that we have a gate of 2 receivers, how do we calculate the detection probability of a fish passing through at X meters per second with a given transmission frequency? To calculate the probability of detection of a passing fish at any point between 2 receivers, we use a binomial probability model that states that the outcome, for example fish detection, will be either a success or failure. The model states the following. What is the probability of successfully detecting a fish given that the tag transmits X times within acoustic range and given detection probability profiles indicated by the blue and green lines? In this example, we will use a fish length of 12 centimeters and a swimming speed of 25 centimeters per second. We assume a tag programming delay of 60 seconds, a VR2W detection radius of 350 meters, and tag detection probabilities indicated by the green and blue lines for good and poor conditions. Knowing these values, we can now go ahead and calculate the probability of detecting a passing fish at any point between the receivers in good and poor conditions. The outcome of the model is shown by the red and pink lines. The probability will range between 0 and 1. As you can see, with a 700 meter spacing, all fish are detected in both good and poor conditions. In this example, a 700 meter spacing would make a good gate design. So now let's see what happens if we increase the spacing. Let's try 800 meters. As you can see from the green and blue lines, the detection probability of a VR2W detecting a tag reduces to as low as 0.1 in the middle between the receivers. So what does that mean in terms of detecting our fish? It means that in this example, there is a small 100 meter corridor in between the receivers where fish are not likely to be detected in poor conditions. In good conditions, all fish are reliably detected. This design still gives good results in most conditions. If we space the receivers even further apart, in this case to 1,000 meters, you can see that the corridor widens and the probability of detecting a fish reaches 0 in poor conditions. In our view, this spacing is too large because some fish may go through and not be detected. In this case, you need to decrease the spacing or put more gates in along the path of the fish. So let's discuss gates in general. This analysis shows that one should think carefully about gate design if you require reliable fish detection. To summarize, if we look again at the 800 meter spacing example, we can conclude that our fish will be reliably detected unless it passes near the midpoint in poor conditions, and it passes so quickly that only a few transmissions will be within acoustic range, and the conditions are not worse than what we have modeled. The simplest and safest approach is to space receivers close enough such that you can achieve close to 100% detection probability in virtually all weather conditions. Before we conclude this presentation, I'd like to show you two examples of acoustic gate construction that you could consider. The bubbles in this figure represent the average detection diameter of each VR2W. In good and poor conditions, the bubbles should overlap such that one achieves close to or 100% detection probability. In the single gate design, you can clearly see that its weakness would be the loss of one or more receivers. In this case, you should not totally rely on this one gate. This staggered double line design requires that one line be offset from the other. This design uses two more VR2Ws than the single gate design, but its advantage is that you still have good coverage if you lose a receiver in the front or back row. To conclude this presentation, I would like to leave you with four main points. Receiver spacing needs to be based on worst anticipated conditions. You may need to derate your range tests if they don't include such data. Don't space your receivers on your best range test data. Make sure you plan for overlap. Degradation of performance is gradual as spacing is increased over our suggestion, but at some point it will be unacceptable. As you increase spacing, you may have to accept that some fish may pass without being detected. Site adherence. Keep in mind that, because of significant range variability as conditions change, the size of the site as seen by the VR2W is not constant. Range is dynamic, changing throughout the day, weeks, and months. And finally, I'd like to remind you that, although one can take an academic approach to designing acoustic gates, it is our view that the best approach is to place your receivers close enough such that passing fish can be detected at almost every time during your